Okay. I will today consider structures for digital filters. Remember, though we considered linear shift invariant systems in general, we then took rational system as an x n y n. We took a special kind of linear shift invariant system, which was a rational system, that was y n plus a 1 y n minus 1 dot 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 a p y n minus p. It was equal to b 0 x n plus b 1 x n minus 1 dot 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 b q x n minus q, and with 0 initial conditions it was linear and shift invariant, and then we found out its transfer function, and since linear and shift invariant, y z by x z gave the z transform of h n, because x z into h z was y z. So, here if you take y z by x z, that is also h z, because this system is linear and shift invariant under 0 initial condition, and then we found out to be of the rational form, a ratio of two polynomials, numerator polynomial by denominator polynomial. Numerator was b 0 plus b 1 z inverse and dot 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 b q z inverse q. Denominator was 1 plus a 1 z inverse dot 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 a p z inverse p. Okay. One reason we choose this special kind of linear shift invariant system is that by choosing a 1, a 2 and a p, these coefficient values appropriately, we can ensure that the poles, that is, if you factorize this denominator polynomial into first order factors, the roots are called poles. So, they depend on the choice of a 1 to a p. By choosing a 1 to a p appropriately, you can make sure that all the poles lie within unit circle, which will ensure causality and stability, which is in general not possible to ensure for an arbitrary h n, because then h n must be causal, that is h n should be 0 for n less than 0 and it should be absolutely summable. But how to impose that, how to enforce that, how to make sure that your chosen h n really satisfies at least the stability part, in general it is not possible, but in this case rational system, by just choosing a 1 to a p appropriately, we have the access to poles here, and ROC is governed by poles. So, all the poles lie within unit circle and the ROC is outside that, which contains unit circle, and you can ensure stability causality. But another very important reason why we choose this model is that we can implement these things in digital electronics, using some basic building blocks. One is a adder. This adder, actually in digital electronics, this when you write an adder, it takes one bit, another bit, 2 bits at a time, and there will be an input carry, then output bit and output carry. But this adder actually is not a single bit adder, and when I say this line, this is not a single bit line. This line can be a bus actually, like this, maybe 16 bits. So, 16 lines in parallel, they are all merged into one line in this diagram, but this is a bus, this is a bus. So, this adder means if there are one set of bit lines for one data, another set of bit lines for another data, then you do addition of the LSB of this with this, then take the result out, then take the carry out, and then add the next to LSB of that with the carry that is coming from the previous addition, then generate new result, propagate the new carry again, like that, the array of full adder is that kind of adder. That is, in terms of digital electronics, it is like this. If this is a LSB and LSB of one data, LSB of another data. Suppose it is A 0, B 0. We have got say A 0, A 1, A 2, 3 bits consist of one word or one bus. So, bus has got just 3 lines. Here also say B 0, B 1, B 2, and if you have to add A with B, this is A, this is B, 3 bit data, you have to add A and B. What you do? You add LSB with LSB, as I told you, with initial carry 0, result and new carry. Then again with this new carry add next to LSB and next to LSB, new result, new carry, like that. And again here this carry goes in, this goes in, and this last bit comes in here, new result, new carry. So, 3 full adders in parallel. So, this total array is indicated by this adder, and this is one line, one bus of say how many, whatever be the number of bits is another bit, but this is only a schematic. This means a structure like this, where there will be parallel lines for the bits of one data, another parallel lines for the bits of another data, and there is bitwise addition starting from LSB and carry propagation. Okay. This is the meaning of this. Then another tool that is used is this delay denoted by Z inverse. This does not mean one flip flop. This means if there are bit lines, say if there are bit lines one, another, say 3 lines. These 3 lines mean actually one bus, and if I delay this means every bit will be delayed by a D flip flop. Okay. This is the meaning of this delay. And another is multiplier. Multiplier, normally these are called constant multipliers. So, there will be a signal line, there is a bus, and this multiplier, there is a built in constant, maybe say A. So, it will be A times x n. So, multiplier will take all the bits of this bus, multiply that with a built in constant. So, this A is not a signal, it is built in. With that, multiply and generate the again result. The result also is a bus. Using them as a basic building blocks or units, we can then construct these filters. This is an IIR filter. We start with that, and then we will consider FIR filters also. So, suppose we have got as an example Hz of the form this B0 say B1 Z inverse, just as an example, say B2 Z inverse 2 divided by say 1 plus A1 Z inverse. I am taking numerator power of Z inverse less than that of denominator, as I told you. If it is equal to or higher than the denominator power, you have to divide the numerator by this, take the remainder on top, and there will be some terms like some constant into Z inverse, some constant into Z inverse 2, and just some constant into Z inverse 0, there is constant only like that. So, they will be realized separately. What I am bothered about is a typical form where numerator degree or numerator order is less than that of the denominator. So, as an example, you consider this 3 terms on the top, and after 1 again 3 terms in the bottom. But this means y z by x z, right. So, x z into this, which means x z into B 0 plus x z into B 1 z inverse. So, this is suppose x z, that is x n, x z into B 0 means x n into B 0, then x z into B 1 z inverse. Z inverse x z means delay of x n by 1. So, suppose it is delayed, and after that multiply by B in B 1, then x z B 2 z inverse 2. Z inverse 2 x z means in time domain x n minus 2. Already I have x n minus 1. So, one more delay, and then multiplied by B 2, and they have to be added, this plus and this plus. So, they get added. So, what is generated here? X z into this numerator, that part is generated. Okay. Now, y z by x z, this means y z is equal to, we want to find out the output y z. So, y z into 1 is x z into this numerator part, that is already available here now, minus y z into this part. So, from this I have to subtract. So, error becomes subtractor actually, because how to do the subtraction? Take the 2's complement of this number being subtracted and then add. These are basic electronic stuff, I believe you all know that. So, x z into this, that is already available here, minus y z into this. Suppose my y z is here, that is in term time domain y z. So, that will be multiplied by A1 Z inverse. So, Z inverse means 1 bit delay, 1 cycle delay, not 1 bit, 1 cycle delay, Z inverse, then multiplied by A1. Then A2 Z inverse 2. So, Z inverse 2 means yz into Z inverse 2 means yn minus 2. So, already yn minus is here. So, this. And then A3 Z inverse 3 means yn minus 3. So, already yn minus 2 is here. So, you have one more delay, multiplied by A3, and they have to be added. So, add with this and then subtract. After you do that, you get yz. So, this becomes your yn. Okay. This relation is the most simplest form of relation, is called direct form 1. I can make a more efficient version of this called direct form 2. In direct form 2, see what is happening here is you are first doing xz into this part numerator. Then in the second part you are generating yz into this part and subtracting, okay, and giving this. So, xz into numerator, numerator means it gives rise to zeros. So, xz into 0, 0 part first here, and the poles which come from denominator, that is second. Okay. That is how it is realized, but I can interchange the two, I will show how, and then I can have a better realization. It will take less number of adders. For that, yz by xz, we write like this, yz by maybe some vz into vz by xz, where vz by xz I take to be, I now first deal with poles. So, 1 by this part. Vz by xz. So, I have introduced a new variable Vz, Vz and Vz cancels, you get yz by xz. Where Vz by xz I take to be, this ratio I take to be 1 by this. So, now this, if I realize this, I will be handling poles only. And the other one, yz by Vz, that will be the numerator, the zeros. So, this will be first, pole first, then zeros, that is interchanging the two there. So, this is equal to B0 plus B1 Z inverse plus B2 Z inverse 2. So, first generate Vz by xz. Vz in z domain means small vz in time domain. Say. So, how to find out Vz by xz? Vz into 1, Vz into 1 is equal to xz into 1 xz minus, you take A1 Z inverse Vz to the right hand side. So, there is minus. So, it is like this, Vz into 1 you keep on one side, on the other side you have xz into 1, so xz minus A1 Z inverse Vz minus again Vz minus A3 Z inverse 3 Vz. Okay. So, suppose here is your xn and that gives rise to xz, xz means xz, that I multiply, that I delay. So, I introduce a Z inverse okay. Suppose I multiply by minus A1, So, minus 1 Z inverse. Suppose I made a mistake. Suppose somewhere or other I have Vz here. Okay. Somewhere or other I have got Vz here. Start from here, Vz. So, Vz somewhere or other I have got say Vz. So, Vz Z inverse into minus A1, that is this. Then Vz Z inverse 2 means one more Z inverse. Into minus A2. After minus has been absorbed in A1, A2, A3, so they have to be added now. So, you add this result, you add with this, and then you add with this. Whatever you get, that is Vz. So, now draw this line. So, Vz generated. This is your Vz. Now, what is Yz? Vz into B0. So, if it is Vz, this goes in this direction also, multiplied by B0 plus B1 Z inverse Vz. Now, Z inverse Vz, you see the advantage is Vz into Z inverse. So, Z inverse Vz is already available. I do not have to apply another delay. Okay. Just take a line out from here, multiplied by B1. And then Z inverse 2 Vz. Take a line out and multiply by B2. And then add all of them. You get your Yn. Okay. If you now compare, you see, you are having the same number of multipliers and adders. That is not a problem as compared to the previous structure. But here you have got adder, adder, and adder, adder, 3 adders. Okay. That I am not having. I am having, you are using delay. How many delay? 3, rather delay is optimized here. This 3 on this side, 2 on this side. But now I am using only 3 delays. 3 delays is actually an array of D flip flops, because this is a bus. So, that is like a shift register, another shift register, another shift register. So, we require less number of delays here as compared to that. If you realize pole first like this, so that by giving xz you generate Vz, Vn, and then from Vz you generate Yz, Vz given you generate Yn. If you do this way, then you save the number of delays. Okay. This is called direct from 2. Okay. Then there are other forms also. Suppose one Hz like that is given, is of this form given B0 plus B1 Z inverse and P greater than Q. So, you can do partial fraction. Partial fraction means you can have some term like say A1, 1 minus A1 Z inverse. Okay. I am assuming first order pole here, and then you will have maybe another term. If this is complex, there must be an A1 star Z inverse, and this also should be star, because then if you combine A1 into 1, A1 in star into 1, A1 plus A1 star become real, because finally my coefficients have to be real, and A1 into minus A1 star and A1 into A1. If it is A1 star, small A1 into capital A1 star and small A1 star into capital A1, they are conjugate of each other. So, when you add them, again you get real. So, if you do this factorization, if you have complex roots, as we know that since the coefficients are real, not complex, then if a root is complex, then we must have a conjugate root also. Okay. And this coefficient was A1. Now, I made the statement that this coefficient should be the A1 star, because then if you add A1 into 1, A1 star into 1. If you add A1 plus A1 star, that is real. Then minus A1, A1 star, small A1 star, Z inverse you take common, and again minus Z inverse you take common. So, capital A1, small A1 star, capital A1 star, small A1. So, and they are added. So, they are conjugate of each other, which means again you get real. So, in such cases, and there may be other terms. Now, in such cases, you do not leave it like this, because if A1 is complex, then if you want to implement it, there will be a multiplier involving A1, but A1 will have its real part and imaginary part. Say A1R plus J A1I. So, even if you are multiplying some real data xn with A1, you will have A1R into this and A1J into this, right, A1I into this. So, two multipliers are required. Multipliers are costly because they require more hardware. If xn also is complex, so it has got a real part, imaginary part. So, you will have 4 multipliers. This into this minus this into this, that will be like xn has got, suppose xr real part n plus jx imaginary part n. If you now multiply this into this, then minus this into this, that will be real part. So, 2 multipliers, and cross terms 2 multipliers. So, 4 multipliers are required. Cross terms will give rise to imaginary part. Okay. If it is real, A1R into xn 1 multiplier, A1I into xn other multiplier, still 2 multipliers, and multipliers are costly. You can avoid them by just using the fact that if there is a root at A1, there is a root at A1 star, and these two coefficients are also conjugate of each other. So, if you add them, this part will give rise to A1 plus A1 star, something real. So, maybe B1. Okay, capital A1 plus capital A1 star, that is a real quantity, a complex number and its conjugate. If you add, you get a real number, call it B1. And then minus Z inverse, if you take common, as I told a while ago, capital A1 into small A1 star, capital A1 star into small A1. So, there again those two quantities are conjugate of each other. If you add them, you get a real. So, maybe B1 plus, I am absorbing the minus sign into the coefficients into Z inverse, something like this. Okay. So, this is what you get in the numerator. In the denominator, you have got 1 minus small A1 plus small A1 star. So, suppose A1 plus A1 star, or to give some name to it, okay. Say C1. So, C1 and C1 is real, Z inverse, and minus plus mod A1 square, this is again real, call it C2. So, C2 Z inverse 2. So, this is real, this is real, this is real, this is real, that you have seen. So, you record only real multipliers plus something. So, this part means what? This plus other terms, they are all equal to, if you add them, that is equal to yz by xz. So, what is yz? Xz into this plus again xz into next term, xz into next term, all are partial fractions. And then outputs have to be added, xz into this product, xz into next ratio, xz into next ratio, carry out this products and then add. Xz into this means basically it is a filter. Okay. Xz into this means, as though this is a filter, its input is xz, what is the output? If you call the output to be y1z, so y1z by xz is this. I can put plus also, no problem, C2 Z inverse. Okay. So, xz into this has to be found out, xz into this part we will call y1z, xz into next we will call y2z, xz into next we will call y3z, and all y1, y2, y3 have to be added. So, it is like this, and this is a second order filter, and we know how to implement it is direct from 1 or direct from 2. So, what will you have is xn, you have this filter. This you realize in direct from 1 or 2 form. This is a second order filter. Both numerator and denominator are second order, is called biquadratic. Then next, if this coefficient was real, then there is, I mean, you cannot say that there will be another term another root with conjugate value, because this is real. So, in that case we will be happy with just maybe a term like B 1, capital B 1 by just some, not B 1, call it say D 1 by 1 minus D 1 Z inverse, and D 1 is real. So, this kind of terms for this you do not have to combine it with another term like D 1 star by 1 minus small d 1 star Z inverse like here, because D 1 is real. So, for this kind of terms x z into this, you can call it y 2 z. So, y 2 z by x z is this. This again you can realize then in direct from 1 or direct from 2. So, there could be terms like d 1 by dot for all the partial fractions, and their results you add. This is called parallel form. There are parallel filters either second order or first order, and you are passing x n through each of them. It is giving y 1 z, it is giving y 2 z, y 3 z like that, and then adding all the outputs. This is called parallel form. Then there can be a cascade form also. Cascade form means instead of going for partial fraction, you go for a product. So, maybe if you take B 0 out, so 1 plus B 1 by B 0 Z inverse, B 2 by B 0 Z inverse to B q by B 0 Z inverse q, and factorize it. So, maybe numerator will be factors like this 1 minus, we have to give some name, this B 1 B 2 is not, I should have told, we do not confuse with the B 1 B 2 here. I have just here that if you add them, if you want you can make it B 1 prime B 2 prime, because they are defined from this original B 0 B 1. Now, so numerator will be some coefficients, maybe alpha I Z inverse I equal to 1 to how many? Z inverse 1 to Z inverse q. So, there should be q terms, and denominator also j equal to 1 to p 1 minus maybe beta j Z inverse 1. So, p times there is a power will be p. Now, here if they have got a complex root, then its conjugate must be there, take those two. I mean otherwise, if this is real, instead of taking 1, you take 2 at a time. So, and order is in your hand, which to, unless you are considering the complex root where you must take its conjugate root, factor involving the conjugate root, and you can convert into second order forms. So, typically it will be a product of this kind of forms, either second order or maybe first order. Second order means maybe 1 plus some gamma, if you multiply to gamma 1 Z inverse plus gamma 2 Z inverse 2, and numerator will be some I have gone alpha beta gamma, what else is left, maybe lambda 0 plus lambda 1 Z inverse, something like this. This is one product, this is one filter, there will be another filter, this could be a first order also. Depending on how you order them, which ones you take first, which ones you take. So, you can have various possibilities, and it will be a product of this kind of form. So, it is called cascade. There will be one filter of this taking input as x n, then next filter like this, next filter again another form of that kind. This could be either second order like this or maybe first order, where denominator will have Z inverse and numerator will have just lambda 0, no further term. Or each of them you can implement in direct from 1 and direct from 2, and they are cascade. So, overall structure will be called a cascade form. These are the typical structures for IIR digital filters. For IIR filters, we will consider in the next section. Thank you very much.